Welcome to the discussion on the topic horizontal shear stresses in beams. This is part of Unit 3 titled Shear Stresses in Beams, which is one of the component of this Strength of Materials Course 1. So at the end of the discussion, our targets will be to understand the development of horizontal shear stresses in the beams and contrasting between the vertical and horizontal shear stresses at a particular cross section and making use of the horizontal stress equation for the no design connections, right? So we are trying to know basically through this what was the application of this particular horizontal shear stresses, right? So let's see how far we can go through in achieving these targets. Let's look at. So first, let's look at what is this horizontal stress, shear stress that develops, how it develops. Let's look at or focus on that point. Now, normally when you apply any transverse load, beam is meant for carrying the transverse loads. So when you apply this transverse load on the beam, obviously there will be a development of shear stress, shear force and bending moment. At any cross section you take, any cross section, whether XX or Y, any cross section you can cut anywhere and try to see the kind of forces acting on that. One will be the shear force and another one will be the bending moment. Okay, these are the two forces acting at any cross section along the length of the beam you take. Now what these bending stresses will do, the bending stresses so bending moment will do, the bending moment will cause in the development of bending stresses that we have studied in the previous chapter in the pure bending. The bending moment results in bending stresses. Then what about this shear forces? Shear force, if you take alone, the shear force results in shear stress development, right? The transverse shear stress is the transverse force, right? Transverse shear force acting in the vertical line. That causes shear stress, right? This is no is the, now the question is the shear stress developed. Here are two questions we can ask. Where is this? Where is the horizontal shear stress here? We don't find anywhere. So where from it is coming, right? And another point is whether the shear stress that is developed is uniform across the cross section, right? So these are the questions that we have to answer. Let's look at that. Now what happens when you apply a load, obviously there is a development of shears. We are talking about here in this particular context only shear, there is a bending moment, right? So we are talking about the what happens to the um, beam when this shear force is acting, this transverse shear force is acting, right? What happened? So because of this, we just now told there is a development of the shear stress. So now the question is whether they are uniform or not, or what's happening after the development of shear stress. So when there is a shear stress developed, obviously, let's take the small particular small beam. We have applied some concentrated load at somewhere at the center, okay, and let's say that shear force we know this is say 10 kilonewton 10 kilonewton, and you take a particular section yy. Now at this particular section, now if you take that particular cross section and try to draw or represent what are the forces acting on that particular element, right? One will be the bending moment, say m on this side, on the other side it will be m plus delta m. Okay, this is the bending moment. Now what was the shear force? So this is the shear force tau b, right? That's all. But we know whenever there is a shear stress developed, it is always no, to balance this couple created by this, there will be always a complementary shear stress develops, right? So from the principle of complementary shear stress, the horizontal shear stress development will take place. Because of the vertical shear stress, the horizontal shear stress will develop here, right? So from the principle of complementary shear stress, the no horizontal shear stress will come the role into the play, right? Now uh, the variation of the bending stress, what happening is there is a variation here, is a m, here is m plus delta m. So then in other words, what this no horizontal shear stress does is it acts as an equilibrium. It brings the no the unbalanced stresses that are developed from the unbalanced movement. The flexural stresses which are developed due to the unbalanced movement will be counteracted by this horizontal shear stress, right? Right now the so we answered how this horizontal shear stress come into being existence. That's because of the principle of complementary shear stresses, right? Basically originating from the vertical shear stresses only, right? Now the, as we told, the shear force stress no, is not constant. It is no, is not uniform. If you take this particular no, cross section, it is not uniform over the depth. It is no maximum somewhere at the center and almost zero at the bottom and top of the cross section, right? Now to illustrate this, to understand it better, let's consider a small experiment. Let us consider a bunch of planks kept like this. Okay, they may be tied, or they can even left freely, uh, but not fully. Not they should be allowed to act somewhat independent manner, right? Or you can even just left it free. Let's see. Then these planks are kept one over the other, and you put a what do you call, some weight on that, right? So then what happens, there will be a sliding happens between this plank, right? Between one plank to another plank, there is a slippage occurs at the interface, right? Now to prevent that sliding, right, the horizontal stress development will take place, right? Now the if you look at, you can draw a line actually at three different locations and try to examine what happens to this line, right? At different locations, say at the top, at the bottom, at the middle, and you will be able to see that the slippage or the distortion no, will be maximum at the center, and at the top and bottom almost it is not destroyed. The line will be in its place. Practically it doesn't move much, right? So from this illustration you can understand that the distortion will be maximum at the center and it will be zero at the top and bottom. Also, if you look at from the previous concept, when you move topwards, right, after all this development of the shear stress, what it does is no, it will balance the flexural stresses which are no, kept not which are not no, balanced, right? This tau h or the horizontal shear stress, what it does is it will try to balance those unbalanced stresses developed due to the excess bending moment, right? Now when you come to the top, at the interface there is no what you call, there is no slippage. Therefore there is no horizontal shear stress. Not only that, the bending stress beyond this, right? There is no change, there is no variation above this or even below this. So when there is no change in the bending moment or the bending moment remains constant, right, then there is no role for this horizontal shear stress. It doesn't have to balance anymore the horizontal equilibrium. That's why finally we can conclude that the shear stress that's going to act across, across the cross section, no, it is not uniform. It is no varying, no, from the bottom to top, or from the neutral axis to the top, or from neutral axis to the bottom. But anyway, it is maximum at the neutral axis, and no, almost no going to zero at the when it reaches the ends. Okay. Now, having understand this, let's see how this, the shear stress, horizontal shear stress, that can be calculated. Right? Shall we be able to calculate? Now we are not talking. Yeah, no, it's easy to calculate this horizontal stress rather than calculating the vertical shear stress. Right? So how to calculate this horizontal stress? Once is both are same, either vertical horizontal stress or horizontal horizontal. Right? The magnitude is same. So now how to calculate this horizontal shear stress? Let us consider a simply supported beam having a span L, right? Now you load it with some no random way. You can load it, some arbitrary loading you are putting on that. Now what you do is, you after loading, you cut off a section. If you cut away section, you take a section at a distance x and draw the free body diagram of that. So that pre-diagram will be having this stretch of dx, and what are the forces acting on that? There is a moment from this end and there is a moment on this side. These two are not equal. They are not equal, right? It will be changing. We know that the bending moment is changing throughout the length. So this is mx and this is mx plus dmx by dx times dx. Now what you do is, you take I am interested to calculate the no horizontal shear stress, which we are talking about, at a distance y from the neutral axis. So I have taken only that particular area where I am supposed to calculate the shear stress. So tau xy. So as we told, this was the balancing force in the horizontal direction. In the process of balancing the what you call unbalanced forces that are emanating from the unbalanced moments, right? Now we have considered the free body diagram and represented the forces. Now what you do is consider a segment of this element, distance y, right? So if you draw this element in the other direction, right, the distance y above the neutral axis, this is how we can draw the cross section of that particular element, right? So this is at a distance y, and you have a strip. Consider a small strip, right, dy, and this is the width of the at this particular height or depth y. The width of the particular section is say ty. Okay, so this is from y to the to the last extreme fiber, say top, y to y top. This is y top distance. That means both are measured from the neutral axis, right? Now, if this element to be in equilibrium in the horizontal direction, what was responsible is this tau xy. So this makes the things, the whole equilibrium to take place, right? So once we take in a horizontal equilibrium equation, let's apply sigma fx. What are some of the forces in the x direction you take? What are those forces? Right, sigma x times tau ty dy. This is emanating from this particular. We look at this diagram. This is sigma x1 and this is sigma x2, right? So sigma x1 acting towards right, so positive, and it was taken only in this area, right? That is from y to the end of that. So y to y top, sigma x times ty dy, and this one is acting towards left, therefore negative, y to y top sigma x times the width times the because it is acting no, right in the x direction. It is a normal stress, therefore the normal area is taken, that is ty dy, And tau xy, it is no, it was taken in the x direction, so ty times dx. Okay, substituting for the magnitude of the stresses using flexural theory, which means we have already know in the previous chapter we have studied that, right? In the previous chapter we have studied the fluid bending theory, where we have derived this equation: m by I is equal to sigma by y. So from this particular pure bending concept, you can bring the rearrange the terms. In place of your sigma, you can replace with momentum, right? Y and moment of inertia. So you replace that, you will be getting this particular equation. If you look at closely, this term and this term are identical. We can cancel out them. So once you simplify, you will be getting. You are interested, right? No, you bring this. This is the term of our target. So if you bring this to other side, right, you are left with these terms, and that tau xy is equal to dmx by dx, right? 1 by ity, and you will be getting this term. We know that rate of change of bending moment from the shear force bending moment chapter also we learned this. Rate of change of bending moment, right, is equal to shear force at that particular section. So the dmx by dx time is equal to your shear force acting on the section or at the section xx. So if you further simplify, what happens is here you can bring out the constant terms out and keep the rest of the things inside. So in the process you will be getting like this: v by, right, I ty, and you will be getting y ty dy. This is very, because it is varying with the y, so that these terms will be inside of the integration. So finally you will be, you will be getting vx. You can say this whole term as qy, integral y to y top, where y is the distance of the section under consideration from the neutral axis, and the extreme fiber distance from the neutral axis is y top, right? So vx qy is nothing but this particular term is called as qy, and ity, which can be further written as vqi by it, right? So this is the final equation. So you require the shear horizontal shear stress at a distance y from the neutral axis is equal to shear force at that section multiplied by the first moment of area. Integral y dA is something like, right, it is integral y dA is first moment of area, or you can even write this same thing as a y bar. You can replace this as is equal to a y bar. That's what we are doing now, right? First moment of area. So sectional, where T is the sectional width, wherever you take the no, wherever you consider the strip, right, at that location, what is the width that you can take as Ty, and this y to y top Ty dy can be replaced as a dash y dash, right? Like this, as I told, integral y dA must be equal to a y bar, or y bar equal to integral y d by a. That we know from the first moment principle of the moments. We can know that. So a y bar or a dash y bar, you can write either way. So what is this a dash? Is the top or bottom? You can take this section either upwards, or you can top side or the bottom side, right? So from wherever you take, from there to the extreme fiber distance, portion of the members cross sectional area defined from the, right, is the top or portion or bottom portion of the member cross sectional area. So wherever you take from there to the top, or wherever you take from there to the bottom, right, that area we have to take. And y bar is nothing but the centroidal distance of that particular area. Let's say this is the area from centroid of this particular area from the neutral axis you measure. That becomes your y bar or y dash. You can call either way, right? So a dash is that area wherever you are taken section from there to the top, and your y or y bar is the distance of the centroid of the area that you have chosen, right, from the neutral axis. Okay, so with the help of this equation, one can find out the horizontal shear stress anywhere across the depth that you are interested in. Okay, now finally we have left with one more target in our no discussion. What was the role of this horizontal shear stress in the design of various connection, particularly when you are no dealing with the kind of girders, made up of flanged sections, right? In order to find out what is the amount of welding or the material to be applied here, particularly in the welded connections, to decide the thickness of the weld, we require to calculate what is the amount of horizontal shear stress that is developed between the at this junction. Okay, in this direction, what is the horizontal shear stress developed? Right, in that particular context, we may be using this concept that this horizontal shear calculation is essential there. So calculate that, and accordingly we will provide the size of the welding. Right. That's all about this discussion on the horizontal stresses in shear stresses in beams. Thank you.